right, so here's another set. Again, we're doing cantilevers. So I'll tell you that the reaction here on this left side is going to be W naught L, and that the moment will be W naught L squared over 2. Okay? And we're going to use the same relationships we did before. We know that the change in shear is going to be the area under the load curve. So let's apply that first. So my shear is going to start off with what kind of value? What is this? Is this a positive or negative shear?
Positive.
Positive. So I'm going to start off at a value of W naught L. The change in shear is the area in the load curve. What's the area in the load curve? Well, this is negative load, so that's negative W naught times L. So W naught L minus W naught L is 0. We also know that the slope of the curve is equal to the load. And what is the load everywhere? Negative W naught. So a constant slope, negative slope. So if I were to look at this, it would have a slope of negative W naught. And now I have a linear shear diagram. So looking down here at my moment curve, what kind of moment is this to start? Positive or negative? Negative. So we're going to start off at negative W naught L squared over 2. And we know that the change in moment between any 2 points is the area under the shear diagram. Well, that's easy. That shear diagram is a what? Triangle. 1/2 base times height. And it's positive. So 1/2 base L times height, W naught L, is W naught L squared over 2. And that's positive. You add it to the negative W naught L squared over 2, and you get 0. What is the shape of the moment diagram? Well, it's given by the shear. What is the shear value at x equals 0? It's literally W naught L, which is positive. So I'm going to draw a positive slope. What is the shear value at the end of the beam? It's given by that. What is that? 0. So it should have 0 slope. Draw a line that fits that, and you get something that looks like that. There's your moment diagram. Again, you're designing this beam. Where's the maximum moment? At the reaction. And what's the value? W naught L squared over 2. Do you need to know anything else? If you want to make a really efficient beam, you can make a beam whose cross-sectional properties decrease because you don't really need a big beam out here. There's hardly any moment at all. So a lot of times on cantilevers, you'll see a tapered beam, and that's why they're tapering it. They know that the moment's max at the base and decreases to 0 at the end. So the capacity of the beam does the same. That's easier to do in steel than in concrete. Okay, we'll stop here. I won't get a chance to do this one. I'll probably post a solution of this one, or I'll just wait till next time. All right, see you guys Thursday.